So good afternoon, everyone. I'm here to speak about robotics and software, how to develop software for robots. So let me give you a quick overview of my background. I'm French, as you can tell by my accent. And I'm actually a software engineer by training. So I learned software engineering back in France. And at the time, the only software engineering school available in France was actually CRM, or like big software system. And I thought it was extremely interesting, but I wanted to do something a little bit more maker-oriented or technical and involving more sensors or a little bit more complicated. And I went to robotics, and I started doing robotics back in France. Then I moved to the US. I had the opportunity to work at Google Robotics on robots in the robotics division. And then in this wonderful area that is the Bay Area, I had the opportunity to co-found Otto, which is a self-driving truck startup. So another kind of robots, but very big robots. And most recently, of course, I sold the startup to Uber, so worked for Uber for a while, and most recently joined NVIDIA. So, and the reason why I give you all this background is really to tell you that there's a lot of different ways to do robotics. We can do robotics different. There's a lot of different. I'm lost. Sorry. There's a lot like. Software engineering is very different. If you do it for CRM, or if you do it for big system, or if you do it for embedded or for truck, it's all very different. And one thing that is very funny is, if you look into robotics, robotics is also very different. You have a lot of different kind of robots. And as you can see here, I'm presenting some of the robots we're working with at NVIDIA. And so some of the robots are big trucks. Some of the robots have arms. Some of the robots are outdoor. And some of them are for agriculture and need to be very precise and observe the fields very accurately, and of course need to be very dust-proof because there's a lot of dust. Some of them are working more in nurseries or very protected environments, but need to be extremely precise. Some of them are going on the sidewalk and are much smaller scale than trucks. And others are inventory or working in our warehouses to make sure our packages are going to arrive in time. For Christmas or for big events. We have also flying robots. And finally, just robots moving around in different kind of environments. So going from A to B, logistics. So all these robots are very, very different. And ultimately, they all need the same kind of data. They all need to be able to collect data from the environment and to get sensors to be able to observe the environment. And they all need a brain. And the funny part is that when you think about it this way, it turns out all these robots have a lot of things in common, and that they still need this nervous system, and they still need this nervous system to be connected to the brain. And so, robotics has been an overhyped field for about 20 years, like machine learning, by the way. Machine learning is not new. And so, what's very interesting, what's happening right now, which is very interesting, is that with machine learning, we finally have a way to lower the technical bar required to actually develop very complicated applications. So, for instance, when you look at a stock market, or when you look at insurance, or all this area where you have a lot of data, the fact that you can actually have this data and build algorithm by looking at the data allows experts of the field experts to actually develop application. You don't need to be a mathematician anymore. If you have the data, you can train and you can start developing software. Which is fascinating, because when you think about it, it means that suddenly, before in the world, you only had thousands of people able to do the job. Suddenly, with machine learning, you have hundreds of thousands, or even more. And so, and that's why everybody's excited about machine learning, and that's why this is very interesting to see what's going to happen next, because no one knows. And in robotics, here is the funny part. We could say, oh, robotics, the same thing is going to happen. Machine learning is much better, and then suddenly everything is just going to work, because if the brain is better, then we're just going to be able to everybody is going to be able to develop robotics. Yes, but there is a big difference. So in robotics, we have very little ways to capture data. There's very little sensors. Right now, we are extremely gated by the hardware. We are extremely gated by the workflow we have to process data and to get data into the brain. And in the end, if you don't get the data in, or if you don't have a way to gather all this data, and then you don't have a way to actually do any kind of decision based on the data. And so at NVIDIA, we decided to do to take the problem in a little bit different approach to what was done before, which is we decided to isolate in all this kind of robotics problem a common workflow. And what it means is that we are building tools that allows all these robots that we've seen before to collect data in an efficient way, process it, reduce the dimensionality, do machine learning on top of it, and be able to really accelerate development of robotics application by really focusing on building these tools that are common to all the robots. And I keep saying commonality, because what we want to do is really, establish this baseline and build these tools that are common to everyone, so that on top of it, we can start developing applications that are more field-specific. And so, and it turns out it's actually doable, because the number of sensors in the world is limited. And so if we have good processes to capture this data, then we have good ways to accelerate the development of application on top of it. If you have an arm, for instance, and you put a camera on your arm, well, it's not much different to having another camera on a mobile base. What you're going to do in the end, the decision you're going to make is going to be different, but the pipeline to capture the data is going to be the same. So I'm super happy because I'm at a developer conference, so I can be geeky. We have amazing stuff. So first of all, we have, so NVIDIA is a hardware company. What am I doing here as a software person? Well, it turns out that if you really want to do good hardware and good robots, you actually need very good hardware. So we have, at the base of the platform, we support all the hardware that NVIDIA develops, which is, it can be a GPU that everyone knows, but we also have AGX, which are this little embedded computer with a lot of I/Os. On top of that, we have all the low-level libraries to perform different kind of computation. And then we have all of that, which is Isaac. And the way we do it is that we have this Isaac framework that takes care of all the ugliness of developing multi-threaded systems, like message passing, efficient message passing in memory, either with the socket or with shared memory. We have a configuration, an advanced configuration system, which is really allows you to tune your system with only configuration files. We have a node-based component, so you can create, even visually, your compute graph. We have a behavior system, because it turns out that a lot of machine learning or a lot of intelligence is context-specific. We have record replay capabilities, task scheduling, and even distributed compute. So you can distribute your workload across a central node or a central authority in the edge. And so, and on top of that, we provide libraries that are useful for many kinds of robots. And so we have a lot of things that are, of course, GPU accelerated, related to perception. We have navigation and libraries required to be able to move around in your environment. And then we have, of course, advanced visualization. I will show you a video just after. And finally, of course, we have drivers, so that you can plug your sensor and it's just going to work. And the application layer here, this is where you develop. But all the rest should just work. And so all the logic and what is field-specific would happen here at the application layer. And so I'm going to show you a couple of examples on how it works. But first of all, let me also talk about maybe one particular thing that NVIDIA is very good at. It turns out NVIDIA is actually, like historically, a gaming company. And that's actually very good news for our little robots, because it turns out when you do computer vision nowadays, it's pretty much a computer graphics problem. I mean, it's getting more and more like that. I was speaking about machine learning before. 30 years ago, machine learning was working very well already. But we could not make it work for images. And so basically, every single thing that was invented at the time was done without images, which you can think about it is pretty hard. If you are a bat, for instance, it's probably going to be very hard to use only sonar information to actually make sophisticated planning and control in a cluttered environment. So now that we have cameras, it turns out the problem and the development of a robot can be actually approximated with simulation. And so that's what we do. So we developed an advanced simulator where we can actually prototype and do a lot of continuous integration, very boring, but very needed. But also, we will see later, we can also do, it turns out we can also do machine learning using simulation. And so thanks to our toolbox, whatever you do here, when you are in simulation, well, you're going to prototype here on your desktop computer, and then when you're ready, you're going to deploy it. And why is it important is because it turns out if you are a cloud expert or if you work on the cloud, it's very likely that you are not an embedded expert. But with a single framework to do all of that, it turns out we actually have a single language, from cloud to edge, which means that when you think about developing an application, you already you can put yourself in a place where you understand how it's going to be deployed. And so with that, we can speed up the development process, and we can make it more, I mean, we make it easier to deploy to the edge, basically. So here we have a diagram a little bit more complicated about Isaac architecture. And as you can see, we really have this abstraction between sensors and simulated sensors and reality. And so a lot of work and a lot of engineering went into making it extremely easy to do things in simulation, and then basically making sure they work on the edge. And it turns out it actually makes it more fun to develop. Because if you work in simulation, so how many people here work with hardware? All right, you're more on the left than the right. So hardware is super painful. Hardware can be really painful. Sometimes things don't work, you don't even know why. And it could be something stupid, I don't know. USB decided to downgrade from USB 3 to USB 2. And as all your sensors were plugged on the same USB hub, then nothing works anymore. And then it takes you forever to fix that, because at the same time you uploaded your CL, and it turns out you changed something critical on the same on the same component that was using this USB hub. And for robots, you multiply that by the number of sensors you have, because everything breaks all the time. So if you have a simulation, suddenly it becomes much more fun to develop. Because, well, the robot doesn't work, it's fine. I file a ticket, someone is going to fix it. In the meantime, I'm going to fix my algorithm in simulation. And so along this line of making things fun, I'm going to show you one of the visualizations we have working on one of our robots. So again, we're trying to make it fun to gamey, I would say, to develop a robot and to be able to debug it. So you can see here, we have, so this is a web framework. It's fully, I'm not very good with PowerPoint. I have a Linux machine. So you can see here, you have the list of all the components and all the nodes that are pushing data. And so what you see here comes directly from the robot. So you don't have to think about embedded anymore or anything. What you see when you develop your application is this. And so here we have, this is one of our buildings, and we have our robot is actually delivering popcorn from one location to another one. And so you can see that we have the map showing the localization here. We have the path of the, oh, that's the graph, actually. That's the graph that the planner is using to plan a path and to go to another location. We have a 3D visualization here that is more gamey and allows you, very useful if you want to debug sensors placement and all of that, to make sure that you don't get your math wrong in your transforms, you know. And so with this tool, you basically really configure how you wanna, what you want to see, what is interesting to you. And again, it's very important to get these tools, because if you, the dimensionality of data that you have on a robot is so big that if you cannot downscale it to something that fits in a screen, then it becomes extremely hard to debug. And so that's really what we try to do with Isaac. Okay, so we also, of course, develop a couple of what we call gems, which are these very precious libraries that can be even hardware, that can be even framework agnostic. And we make sure we test them very well in the context of an application. So the idea is that we don't throw a library like that, but each single library we have here is a library that you can embed in the compute graph and that we make sure works well with the rest of the ecosystem. So here, for instance, we have, okay, global localization, how to find, how the robot, when it opens its eyes, can find itself in a location. We have LQR planner, which is just a way to make sure the robot is going to go from A to B. That's something that is used also in self-driving cars, by the way. We had it on trucks before. We have a stereo vision algorithm that are optimized for GPU, and we have several variants of them. We will see after. We even have a neural network version. Pose estimation, physical pose estimation, people detection, map editor, so you can really customize where the robot can go. Visual odometry, physical simulation, gesture recognition, and even sound processing. So many things. So here is a very interesting workflow that we introduced. So as I mentioned before, now that we have simulation and that we increasingly use video and camera to perceive the world, it turns out we can actually learn a lot from simulation. And so what we developed is a way to create your scenarios and introduce domain randomization to at least bootstrap the training of your algorithm. And it's a big deal because right now it turns out labeling and making sure your labels are correct and making sure that the labels are actually error-free and formulated correctly is extremely time-consuming, especially for robots, where you really have to drive the robots around in the field, then collect the data, then send them somewhere, then get them back, then figure out the annotation is wrong or the label is actually wrong. We needed something else, and so and back and forth. So here with simulation, you can actually directly train you can validate your hypothesis at least. I mean, at the very least. But even more, it turns out if we train inside your compute graph, if you really use the same blocks in your compute graph, so basically instead of taking the raw image, let's say you need to do a transformation before to put it on the floor or to have a top-down view. Well, if you can train inside the framework, inside Isaac, you can always put the plugs and capture the data anywhere in your system, which helps having a very systemic approach to machine learning. And it turns out it helps a lot generalizing. It helps a lot transferring from simulation to reality. And so a couple of examples that we did here. We do that currently for stereo. It turns out we can teach the robots to do stereo. And that, of course, would be very hard to do if you had to label it by hand. Or you could use a laser, but then you would have a density problem. But with simulation, you have the data for free. And we do that also for object detection. So for object detection, it's a little bit different. We actually have a pre-trained YOLO model. But each time you want to teach it new object, you inject objects in the simulation, press a button, and then it's going to just magically work in reality, which is pretty cool. Very quick app example, so we have time for questions. This is an example of one of the reference designs we have. We work a lot with reference design. I mentioned it before. The reason is if we don't test it, if we don't test the full system working by ourselves, it's very unlikely that we make micro-optimization on part of the system that are not really necessary for the overall behavior. So we have a very simple delivery robot here that works called Carter that work in reality and in simulation. And so I'm going to show you what it looked like, what we did with Slack. Now, if you are very good, you can retrace the past and find it. Thank you. And, oh yeah, last slide, GTC. We have a GTC very soon. If you want to see more robots, feel free to join us. And we will present much more, many more goodness. But in the meantime, I would like to spend the rest of the time for a couple of questions. Yes? Oh.
So where does ROS fit into this? I mean, are you actually using Gazebo? Are you using Arvis to do the simulation?
That's a very good question. So I think the diagram actually was not very accurate. I would see more ROS side by side with Isaac. We have a very similar component-based architecture. So we have wrappers, and we just you just write wrappers. Like the main thing that you need, so the main thing you need to do if you want to couple a ROS system with Isaac is basically make sure that the serialization you use is converting the message into the right format. Because we have another serialization protocol. But otherwise, it's very similar. Yeah. And all the rest of the tools is developed from scratch. And the reason is because we need to do cross-compilation. So we need to be able to have a very compact code base. So no boosts, no external libraries. We need to be extremely tight in what we deploy.
So Isaac is, you can actually say it's a competition to ROS.
I think they have different purposes. I can see how both are useful. There's things that ROS does that we don't do, and there's things that we do that ROS doesn't. So yeah. Yes?
Today, you have to train the robots for the actual user environment they'll be placed into. That adds a lot of adoption challenges. So how do you see a future where they'll become more general purpose? You don't have to actually train them in the actual hospital or the warehouse.
Yeah. So let me give you a more detailed answer. So 80% of the stack would work without training. And it's actually not even machine learning. It's just traditional computer vision and math. And the reason why is because a lot of problems are very well known. They've been solved before. And what we try to do is making sure that these problems that were solved, we have industrial-grade solution for them. And we give them to everyone. Now, the problem is that even if you have 80% of the problem solved, you still need the 20% remaining. And depending on the application or depending on the problem space, it can take years to solve them. So what we do is we make sure that we have all these tools and these machine learning tools and these behavior trees and this simulation so we can speed up this part and make it easier to build custom solution. Which we will never do at NVIDIA, of course, because we build the platform. And so it turns out that for machine learning, it's very good, because we know that it's pretty hard to generalize everywhere. And it's not necessarily a problem for robotics, because it turns out robotics is always field-specific. If you build a robot, it's to do something very, very well. Well, I mean, most of the time, unless it's Terminator, but then it's a very complicated problem. But otherwise, you are always very context-specific, and we believe that the key is to help you solve this context-specific problem in the minimum amount of time. That's why we build the tool around. Other question? Thank you.